Hi everyone. So today I'm going to tell you about some new work where we're characterizing chaotic dynamical systems as intermittently forced linear systems. So we take chaotic dynamics and represent them in a linear system framework using modern Koopman operator theory. And we'll find that these systems are intermittently forced, corresponding to rare events like lobe switching in the attractor of the Lorentz system, or bursting, or other intermittent phenomenon. So it's a data-driven decomposition of chaos into a linear system that is intermittently forced. This is work with my co-authors Brunton, Josh Proctor, Eurika, Kaiser, and Nathan Kutz. And before I jump in, I just want to say chaotic dynamical systems are everywhere. They describe lots of fascinating phenomena in the world around us. So the climate, turbulent fluids, the stock market, disease spread, the motion of planets are all chaotic dynamical systems. They're very well studied, and they've fascinated people for a long time. So we've spent a long time thinking about chaotic dynamical systems. Interestingly, chaos is not random at all. This is a kind of an early misconception, but chaotic systems are, in fact, highly structured, and there's lots of patterns. So this Lorentz example, attractor is a good example. There's lots of structure in this chaotic system, and we'll get into what chaos means a little bit more later. So before jumping into the new analysis, I just want to give a recap. So dynamical systems history. So the original kind of classic view of dynamical systems, you have x dot equals f of x. X is the state of your system. This is some system of coupled differential equations, probably nonlinear. And you're interested in understanding what initial conditions do in this system. So where do trajectories go? If I have all of the planets right here, right now, where will they be 100 years in the future? Okay, so you want to be able to predict by integrating the initial conditions through these dynamics. So that's what we're doing over here. And you can use that to get a discrete time update where you go, like, what's my system at time now? And it tells you what your system is at discrete measurements in the future. This is the classic geometric view, all the way back to Poincaré, and it's concerned with how trajectories are organized by things like saddle points and periodic orbits and attractors. So geometric organization of trajectories in the dynamics. The more modern kind of Koopman operator perspective is that instead of propagating the state of the system through these nonlinear dynamics, it's possible to consider measurement functions of the state. So here we have g is a function that measures my state. It could be sine of the first component or the second component cubed or something like that. And so there's this infinite dimensional space, this Hilbert space, of all possible measurements I could take of my system. And so this Koopman operator k, it always exists, and it's linear, and it maps my measurement function g at time k, tk, to the next instance in time, tk plus 1. So if I have my measurement g of my state at time k, and I hit it with the Koopman operator, it advances that measurement to time k plus 1. So this always exists, it's linear, but it's infinite dimensional. So we're trading finite dimensional nonlinear dynamics for infinite dimensional linear dynamics in this Hilbert space of all possible measurements. Now, Koopman actually came up with this quite a while ago in 1931, but it's only been recently kind of developed and really applied in lots of systems due to the pioneering work of Mezich and Rowley and collaborators, where they're really taking this data-driven perspective. Okay, so in lots of systems of interest, maybe a turbulent fluid in a jet engine, or the climate, or the stock market, we might not even have a good representation of the full dynamics, but we have tons of data. And so building up approximations of this Koopman operator from data is a very promising modern field of study. And just to remind you, these systems are hard to work with. They're nonlinear. They might not even be very easy to solve and integrate. linear systems, if I can get this Koopman linear representation, I can do all kinds of things that are standard in linear analysis. I can do future state predictions, optimal estimation, optimal control. Basically, it just reduces this to a linear algebra problem, which is great. And the perspective we've been taking in recent work is that to get a good approximation of the Koopman operator, a finite dimensional approximation, you need a Koopman invariant measurement space. So this is a subspace of your infinite dimensional Hilbert space of possible measurements, where if I took a measurement of my system in this subspace and I hit it with Koopman, I would stay in the subspace. Okay? If I have that kind of an invariant measurement subspace, if I restrict my Koopman operator to that subspace, I get a finite dimensional linear operator, a matrix K, and I get a linear dynamical system that propagates those those measurements, those good measurements forward in time. So I can do linear optimal control, optimal estimation, future state prediction. The trick here and the problem is that finding those invariant measurement subspaces might be exceedingly difficult. Those invariant subspaces are related to eigenfunctions of the Koopman operator, and these might be very difficult to find, hard to represent, and they carry as much information as the full solution of the dynamics in some cases. Okay? So finding good invariant measurement subspaces is critical because there's so much powerful theory and analysis that you can do once you have a linear representation. So I'm going to tell you about this new analysis that we have, and I'm going to demonstrate it on the Lorentz system because this is really a good toy problem that illustrates chaos. It's very well studied. So here I took an initial cube of trajectories and I'm integrating them through. You see that very rapidly these trajectories stretch and kind of mix on the attractor. And so this is kind of a graphical illustration of the sensitive dependence of the Lorentz system to the initial conditions. So that little cube of red initial conditions was all pretty close, but after a short amount of time, they get stretched and folded, kind of like taffy, and spread onto this attractor. Okay, so this is the prototypical example of chaos that we're going to analyze. And what we're going to do is develop this new view of Koopman to get invariant measurement spaces that we're calling the Hankel alternative view of Koopman, or HAVOK analysis. Okay, and we're going to demonstrate it on Lorentz. So we take the Lorentz system, and the first assumption is that maybe we don't have access to all of the measurements of our chaotic system. Maybe we can just measure a time series of x. So this is what the time series of x looks like. When it's up here, it's on one lobe of the attractor, then it's on the other lobe, and it switches. And the switching is maybe hard to predict. So we measure a time series of one variable x. We build a Hankel matrix, this H matrix here, by taking the time series and then time shifted copies. So T1, time 1 to time p, time 2 to p plus 1, 3 to p plus 2, and so on. I stack those as rows of my Hankel matrix. And then I take the singular value decomposition of this Hankel matrix and I get eigen-time-delay coordinates. I get these eigen-time series that are ordered from most important to least important and their ability to express this data. Okay, so I get these eigen-time series in the columns of U and the columns of V. And those are the time series that are most self-similar to the time series that we use to train this model. Okay? This idea of building a Hankel matrix and taking the singular value decomposition is not new. It's used in the eigensystem realization algorithm. It's used in the singular spectrum analysis in climate. There's recent extensions of SSA by Giannakis and Maida, the nonlinear Laplacian spectral analysis, which is a really neat, modern, data-driven kind of view of these Hankel matrices. But the upshot is, once I have this data and I build a Hankel matrix and I take my singular value decomposition, I get a good measurement system, a good set of delay coordinates, where if I plot my trajectory in these new delay coordinates, this delay embedding gives me an attractor which is diffeomorphic to my original attractor. Okay? And again, this is not new. This goes all the way back to Hawkins, who is studying this in the context of turbulence. And many, many people, many more than in this list here, have analyzed time delay embeddings for nonlinear systems. And so what I'm actually plotting here, the columns of V are time histories of the first eigentime series, the second, the third, the fourth, and so on. And I'm plotting those time histories of the first 3 eigentime series. So this is V1, V2, V3 coordinate system, and this is my data in that coordinate system. So I'm literally just plotting the first 3 columns of V. And what's really neat is that there's a connection between this data-driven, the singular value decomposition of the Hankel matrix and the Koopman operator. So I can take my Hankel matrix, and instead of writing it x at time 1, x at time 2, time 3, time 4, and so on, I can instead write it in terms of iterates of the Koopman operator. Okay, so remember, Koopman acts on measurements of the state, and this is just a measurement of the x component of the state. So I can take x at time 1. If I hit it with Koopman, I get x at time 2. So this is x at time 2. If I hit it with Koopman again, I get x at time 3, and so on and so forth. So I basically get this series of increasing powers of the Koopman operator applied to x at time 1. This is another view of the Hankel matrix. And what's really neat is that when we take the singular value decomposition of this Hankel matrix, we find that even though this thing has lots and lots of columns, in this example for the Hankel matrix, maybe I have 10,000 columns, I get low-rank structure that emerges from the singular value decomposition. And I might find, for example, that the first 15 columns of U, of this U matrix and the singular value decomposition, the first 15 columns are adequate for describing all of the columns of H. So every column of H, up to numerical precision, is linearly dependent on the first 15 columns of U. Very cool. And what this means is that essentially the second column of this Hankel matrix is just Koopman acting on the first column. The third column is Koopman acting on the second, and so on and so forth. I act on all of these columns by Koopman, and I get the next column. And what that's telling me is that these 15 leading columns of U, these leading eigen-time delays, are invariant to the Koopman operator. Because if I, at least for data on the attractor, that's not true for all data, but for data on the attractor, if I have one column and I hit it with Koopman, I'm still going to be in the span of U. So this is a Koopman invariant measurement system given by eigen-time delays of the Hankel matrix. And it's data-driven. Very, very cool. Okay, and again, this is where the Hankel and the Koopman in the HAVOK model come from. So the fact that we have this connection with the Koopman operator, we can represent the Hankel matrix in terms of the Koopman operator. We get this data-driven basis for making the columns linearly dependent and giving us an invariant subspace. This all motivates building a regression model on these time delay coordinates because we probably have a linear system underneath in the right coordinate system. That's what Koopman tells us. And this is related to the dynamic mode decomposition and the sparse identification of nonlinear dynamics, which are regression methods that take data and give you models. Except here, we're doing this linear regression fit on these eigen time delay coordinates from the SVD of the Hankel matrix. And so what we find is that right off the bat, we can build this linear regression model. It's super simple in MATLAB, basically just the backslash of the pseudo inverse. So we build this linear regression model that best maps, that best describes these columns of V. And what we find is that the first r-1 delay coordinates are very well approximated by a linear model, this linear part of this linear model up here. The last time delay coordinate, in this case the 15th time delay coordinate, does not have a very good fit. The v dot equals equation for the 15th time delay coordinate is not very good. Even if I include nonlinear terms, it's not great. So what we decided was, let's act like this last time delay coordinate. Let's not try to model it. Let's say it's an external forcing. We can measure it by, if I'm measuring a streaming set of data, I can measure what my VR coefficient is. Let's have that enter as a forcing term to this linear model. So I have a linear model, kind of v dot equals AV plus B times this forcing term. Okay, and here in red, I'm showing a little snippet of that VR forcing term for this data. And you see that it's mostly quiescent, but every once in a while it bursts. It turns on, and then it goes off again. So if you run that intermittent forcing into this linear model, what you get out is a prediction of what the dynamics of the system are doing. That's plotted here in blue, linear dynamics. The blue is our prediction based on this regression model, plotted on top of the white, which is actually the data. So you get a very good linear model prediction if you give it the right intermittent forcing. And so if you run this for enough data, you can build a reconstruction that looks very similar to this embedded system, except our blue manifold is really coming from linear Koopman dynamics with this special intermittent forcing signature. Okay? And what's interesting is you actually see that this intermittent forcing signal, if you look at its probability distribution in the very lower right, it's non-normal. So the Gaussian is the white dashed line. It's very non-normal. It's got these long tails corresponding to rare event extreme forcing. So when these red signals get really big, that's rare, and it's non-Gaussian. And it happens to correspond to when the Lorentz system is about to switch to the other lobe of the attractor. Okay, so whenever this red signal gets big, my system switches to another lobe, which is very cool. So we're going to look at that again in a minute. And this is similar to ideas of intermittent forcing and extreme rare events found in work by SUBSPACES and MIDA and others, looking at things like climate and extreme ocean waves and things like that. So there's some really neat work out there looking at intermittent forcing. And we're taking and looking at this intermittent forcing for this Koopman linear system. Okay, so you can take all of the pieces of that HAVOK analysis on Lorentz. You have the system, you measure some aspect of the system, you build time delay coordinates and get an embedded attractor. You can then build a linear model with a forced linear model. You get a good and reconstructed attractor when you do that, and you have some forcing statistics. So we have gone through and actually applied this HAVOK analysis to lots of systems, from classical chaotic system like Lorentz and Rossler, to kind of mechanical systems like the double pendulum, to more real-world relevant systems, like we have time series data for a model of the Earth's magnetic field switching. So this happens every once in a while. ECG electrocardiogram data for heartbeats, EEG electroencephalogram for a patient that's asleep and their brain is being measured, down to measles outbreaks. So this is real historic measles data from New York City. So you can apply this HAVOK analysis to all of these systems, and you get very interesting predictions. And you can download all of the code and look at any of these examples more yourself. But we're going to dive a little bit more into Lorentz system here, because what I really want to show you is that these HAVOK models are actually predictive. They're predictive of lobe switching. So here I'm plotting the V1. This is the leading delay coordinate in time. VR is the forcing term. This is like the 15th eigen-time-delay coordinate. And I choose 15 using the optimal hard threshold of Gavish and Donahoe for the SVD. And then in the bottom plot, this is the forcing squared, so that it kind of stands out a little more and is positive. And what you find is that most of the time the forcing is inactive, it's small, and that actually means the system is really well described by a Koopman linear system. So all of these white regions mean the system is essentially linear. There's not really any forcing happening. And then every once in a while you get these bursts, these big bursts of activity in the forcing that we color code in red. So anytime this is larger than some threshold, we color code it red, and then we code our trajectory when that forcing is active. And what you find is that when the forcing is active, it actually precedes a lobe switching by one whole period, by one whole revolution of the lobe. So you get this great prediction when this red signal comes on that the lobe is about to switch, which is great. And it's not perfect. We don't capture every single one of them, but it's pretty good. It's pretty predictive. Okay? And you can take those red regions and actually color code the embedded attractor by whether or not the forcing is active, that's red, or whether or not the forcing is inactive in white. And so fascinating, the white region here is really very well described by this Koopman linear system without forcing, because remember, forcing is small. And these red regions correspond to when forcing is large, when forcing is active. So we get this nice linear model in white that actually characterizes the interior regions of both lobes, which is fascinating. And then these coherent regions in red, which tell us when we're about to switch. And so I like this plot because it's kind of the skeleton of this behavior. So let's say we start, this is real data from Lorentz, color-coded by the forcing. So let's say we start the trajectory at point A. We do 4 inner revolutions on the right lobe, and the system is linear, essentially kind of Koopman linear. And then at point B, our forcing spikes. And this is something you can measure. You're measuring your time history, you're convolving with the columns of U from the SVD, and you're measuring this forcing signature. When the forcing gets large enough, that's at point B, we know that the system is about to switch. And we have an entire other extra revolution before the system actually switches. So we get this whole prediction window where we know the system's about to switch. It does, in fact, switch over to point C. The forcing becomes small again, which tells us, hey, we're going to be here for a while. And then we are in this Koopman linear system for 3 more revolutions until point B when the forcing goes up again, and we know that we're about to switch another time. So very cool, very predictive, and easily interpretable and measurable. Okay, so again, we've applied this to lots more systems. We encourage you to download all of the code here. You can try all the examples yourself. Again, this is another piece in this puzzle. We want to go from data to dynamical systems. We have to measure the right things, and now we're learning from like Tocken's embedding theory and observability theory, what to measure, what are good measurements. We need good representations where the dynamics become simple. This is where Koopman comes in, and time delay coordinates. So good time delay coordinates give us a good representation of our dynamics that are essentially linear, or at least in large portions of phase space. And then regression is somehow the easy part. We have lots of powerful tools for machine learning to get models once we have good representations and good measurements and lots of data. Okay, thank you very much. There will be another short video showing kind of more examples and more details about this method. Thank you.